Welcome, dynamic students. This mini lecture is a real quick demo problem taken from the topic of rigid body planar motion kinetics. And it's an example of how we can use our very basic understanding of related rates, something that we all touched on in calculus, probably did a few word problems in calculus, to make relationships between rates of motion, related rates, for rigid bodies a lot simpler. So this is just a little example of it. So we have a horizontal rod AB, and it's going through this sleeve bearing attached to a surface, and this sleeve means that rod AB stays horizontal. So no rotation at all. No, so those both the angular velocity and angular acceleration of AB are zero. So basically, if we were to relate the velocity of point B to the velocity of A, using our general relationships for 2 points on one rigid body, we could write all of that out and say, oh, that's zero. So VB equals VA, and the same holds true for acceleration. So that's what's happening because we have this sleeve that is basically getting rid of our angular acceleration and angular velocity. So it's straight line translational motion for rod AB. So what that means is we've really got a problem that involves only two rods. We've got rod B, C, and we've got rod CD, of which D is a fixed pivot, so it didn't go anywhere. But kind of more importantly, we can also relate, because we know point B can only have motion in the j-hat direction. More importantly, we know something about, I guess, combine that with a fixed pivot. So point D isn't moving anywhere. Point B can only move in the i-hat direction. So if we were to take a look at this distance x between B and D in the i-hat direction, D is not moving. B can only move in the i-hat direction, so we can immediately relate x, or x's motion, to the motion of point B. So we could say, for instance, that the time rate of change of that distance x is equal to, we'll call it probably negative, because if B has a positive velocity, then x is going to get smaller. So we could say is equal to negative VB. So faster B is going, the faster x is shrinking. Furthermore, we could take a look at theta, which is also theta over here, because these two angles are the same, and these two, we have an isosceles triangle. That's why those two angles are fixed and have to be the same. So we can use some trig, and we can relate the time rate of change of those two angles to the time rate of change of x, just using some trig. So we can say, for instance, get a relationship between x and theta. So we can say, in this case, x over 2 is equal to 0.3 meters times, whoops, cosine theta, just plain old trig, x equals 0.6 meters cosine theta. And we'll take the time derivative of that. Dx dt equals negative 0.6 meters sine theta d theta dt. Wow. That is something that we can relate basically to the rotation of one rigid body or the other. So that's something to be looking out for. Now, we don't want to make statements about that for rod BC. Just because we know something about the time rate of change of that angle doesn't mean we know the angular velocity of that rod, because it can move any which way. It's not pinned. But over here, where we've got a fixed pivot, then we can definitely say, because the velocity of d is 0, it's staying still, so the angular velocity and acceleration are definitely going to be given by the first and second time derivative of this angle. And since these two are the same, we should be able to make some relationship between the two. And in point of fact, I believe that was what the problem was asking. We'll highlight it in red. We were asked for the angular velocity and acceleration of CD, which once we have that, we can use our general expressions for velocity and acceleration of point C, and what we know about velocity and acceleration of point B, that we could get angular velocity and acceleration of BC. But for now, let's just look at what we can do with related rates without having to invoke our 2 points on a rigid body motion that are more complicated. Okay, so going back to our related rates expressions, we're going to say that our VB, negative VB, is going to be equal to the first time derivative of x, which is going to be equal to, which from down here we'll bring that up, 0.6 meters times sine theta d theta dt. And we can take the next derivative, start looking at accelerations. So the second time derivative of this dimension x, you know, how quickly it's the rate of shrinkage, is going to be equal to negative AB, which is going to be equal to the time derivative of this expression. So we're going to have to invoke derivative of a product. And so we're going to end up with basically, just going to write that out, negative 6 meters cosine theta times d theta dt squared, which is not d squared theta dt squared. This is just the square of the first time derivative plus negative 0.6 meters. Running out of room here. Let's see if I can budge everything over. There we go. So we're just kind of working off of this. Negative 6 meters sine theta. So we're just continuing to do the derivative of a product times, now we have the second time derivative of theta with respect to t. So we basically just took the time derivative of this expression here. We took the next time derivative of everything. Okay. So if we take a look at rod CD, because we got a fixed pivot, d theta dt is equal to, I'm just going to say point D equal fixed pivot. So we can say VD equals, equals AD equals 0. So d theta dt equals omega dc and d squared theta dt squared equals alpha dc. So if we go back to these two expressions and we say theta equals 60 degrees, because the question is concerned with the snapshot in time at which theta equals 60 degrees, and we use what we know about the velocity of point B, because we were given the velocity of point A, and we know velocities of points A and B are the same, and I'll scroll back over there. So the velocity of point B is 10 meters per second in the negative I hat. So I'll just write this over here, and I can scroll back. So that's negative 10 meters per second I hat is B sub B, and A sub B is positive 16 meters per second squared I hat. I hat. I'll move that back over. So we can go ahead and solve and end up getting, in this case, we'll end up getting a d theta dt in radians per second. And if we just input our 10 meters per second, rectify the signs, we're going to end up getting our, make sure I write this correctly, excuse me, we'll end up getting a negative 19.2 radians per second. So that means basically it's rotating like that, omega, and then if we substitute in up in this expression, we're getting a little messy here, we put in our 60 degrees, we put in 19.2 radians per second for our d theta dt, 16 meters per second squared of acceleration of b. We can isolate d squared theta dt and end up getting a value of negative 182 radians per second squared. This is a little bit messy with all the substitutions, but important points. First and foremost, we invoked what we knew about rigid body motion. We used the sleeve and said, aha, somebody gave me linear velocity and accelerations. We got meters per second squared of point A. This sleeve means rod AB is not rotating, which means the velocity of B and the velocity of A, because we have rigid body planar motion, they have to be the same. Great. That means I can basically get rid of rod AB. So that moves me over here. Now, to be fair, I could use my VC equals VB plus omega BC cross R B to C, and then likewise for CD, put the two together, solve for multiple equations and multiple unknowns, and get my angular velocities of both rods that way. So I can step my way through those basic equations relating the motion of 2 points and do the same with acceleration. It's a lot of math. You get up into that 4 equations and 4 unknowns. Or I can use the geometry of the problem and my related rates expressions here. Put these in green. These were my shortcut kind of get out of jail free cards that got me out of a whole lot of math. I was able to relate the motion of this point, which I knew, because rod AB is only moving translationally. I could relate that and the fact that B is a fixed pivot to an expression for a change in an angle that directly gave me alpha and omega of this rod, which was what I wanted. If I wanted to at that point, I could apply that to get, knowing that velocity and acceleration at point D is 0, I could apply my general equations for velocity and acceleration of 2 points on a rigid body to body CD. I could get the velocity and acceleration of point C, and from that I could get omega and alpha of BC. As it turns out, the problem had only asked for CD. But the key there was I got out of a whole lot of cumbersome math that would have gotten me there at the end by recognizing that I could relate velocity to this dimension, which was in turn related to these angles, which was in turn related to the rotational rate of CD because I had a fixed pivot at D. So there's a lot of related rates, but the relationship of this dimension to some angles and to the velocity of a given point, that is kind of a classic calculus related rates problem. But it works really, really well when we're looking at relating the rates of motion of given points on more than one rigid body and not having to work our way from one point on one rigid body to another point on the same rigid body to another point on another rigid body, which we can always do, but it's pretty cumbersome. So this was a great shortcut to that, using something that's totally valid, and kind of an approach that we've all used in our study of related rates in calculus. So this is a good example of kind of a more general. We had a fixed pivot, but we also had a non-fixed body going. So this, I believe, is in the Hibbler absolute motion section, and it is for reference if you want to go back and look at it and work through it. It's problem 1642. In the Hibbler Dynamics book, 14th edition. So 2 ways to get there. You can check yourself if you want to go back and go from point B to point D using just your velocity, 2 points on rigid bodies working from B through C to D. And getting, I believe you'll end up getting 3 equations and 3 unknowns. But acceleration is a lot more math. So related rates, shortcut strategy, very effective. And there's no reason not to look out for this. There will be various problems you'll do in practice and in coursework where if you can see and verify one of these relationships, it can make a great shortcut. If you get bogged down in longer math or just simply to use as a check. So that is it for this mini lecture, and we'll continue with some more lectures and demos continuing on in rigid body kinematics and kinetics.